Welcome! Today, we are exploring the fundamental physics of how things move. We will uncover the secrets of distance, speed, and kinematic equations. When an object, like this car, moves strictly along a straight path, we call it linear motion. It is the simplest form of movement. To accurately describe an object's position, we must choose a fixed reference point, or origin. Directions from this point are indicated using positive and negative signs. Distance is the total length of the path you travel. Displacement, however, is the shortest straight-line net change in position from start to finish. To figure out how fast an object is moving overall, we calculate average speed. It is simply the total distance traveled divided by the time interval. Let's solve a historical problem. Two postmen are 210 yojanas apart, walking towards each other at 9 and 5 yojanas per day respectively. Together, they cover 14 yojanas a day. Dividing the total 210 yojanas by their combined daily speed gives us the required time. Simplifying the fraction, we find that the two postmen will exactly meet each other after 15 days of walking. When we care about direction, we use average velocity. It is the object's total displacement, s, divided by the time interval, t. Sarang swims to the end of a 25-meter pool and back in 50 seconds. His total distance is 50 meters, but his displacement is 0. Let's calculate the average speed. Dividing his total distance of 50 meters by his time of 50 seconds gives an average speed of 1 meter per second. Because he returned to his exact starting point, his displacement is 0. Therefore, his average velocity is 0 meters per second. Acceleration measures how quickly velocity changes. It is calculated as the final velocity minus the initial velocity divided by the time interval. Acceleration is considered constant if the velocity of an object, like this car, increases or decreases by the exact same amount during equal time intervals. Let's analyze a bus accelerating from 36 to 54 kilometers per hour over 10 seconds. We convert these speeds into standard SI units first. Substituting the initial velocity in meters per second, we divide the change by 10 seconds, yielding an acceleration of 0.5 meters per second squared. Later, the bus brakes to a complete stop in 5 seconds. This negative change in velocity results in an acceleration of minus 3 meters per second squared. Consider a falling object. Gravity pulls it down, continuously increasing its velocity to 9.8 and then 19.6 meters per second at each successive second. If we calculate the acceleration for the first second and second second, we find a constant increase of 9.8 meters per second squared. This represents standard gravitational acceleration. Position time graphs visually map motion. A straight, sloped line indicates an object moving at a constant velocity, while a flat horizontal line means it is at rest. The steepness, or slope, of this line determines how fast the object moves. We calculate this velocity by dividing the change in position by time. Velocity time graphs shows velocity changes with time. A straight, upward-sloping line shows constant acceleration, while a flat horizontal line shows constant speed and zero acceleration. To find the total displacement from this graph, we simply calculate the geometric area enclosed between the velocity line and the time axis. Let's derive our first kinematic equation. We begin with the standard definition of average acceleration, where a equals v minus u over t. By multiplying both sides of our equation by t, we clear the denominator. This mathematical step leaves us with a t equals v minus u. Finally, we rearrange the terms to isolate the final velocity v. This gives us our first primary equation, v equals u plus at. Moving on to the second equation. Displacement is the area under a velocity time graph, calculated as a rectangle's area plus a triangle's area. From our first equation, we know v minus u is equal to at. Let's substitute that directly into our displacement formula. By multiplying the two time variables in the last term together, we finalize our second kinematic equation, s equals ut plus 1/2 at squared. For our third equation, we need to eliminate time. We isolate t from our first equation to get v minus u over a. Now, We substitute this specific expression for t everywhere it appears in our second kinematic equation. Expanding the terms, we distribute the initial velocity u, and we expand the squared binomial fraction carefully on the right side. We simplify the acceleration variable and find a common denominator of 2a. This allows us to combine the entire expression into one fraction. After canceling opposite terms and moving the denominator across the equal sign, we isolate v squared to reveal our third and final kinematic equation. When an object moves in a circular path with a constant speed, like this satellite, it undergoes uniform circular motion. Completing one full revolution yields zero displacement. Because the path is a circle, the total distance is the circumference, 2 pi r. Dividing this by the time period t gives us the average speed. Even though the speed is constant, the satellite's direction continuously changes along the tangent in the direction of motion. Therefore, uniform circular motion is always considered an accelerated motion. That concludes our exploration of motion. Thank you for learning with us today. Keep observing the physical world around you. See you next time.